Okay, so this is a supplementary lecture on the solution of state equations. So let's get started. Solution of state equations. Okay, so let's focus on an example. So let's assume that this circuit is given to me. L, R, and C. Okay. Now the question is the analysis of this circuit, formulation of the equations representing this circuit, and so on. But before everything, so let's think about the order of the circuit. So this seems to be an RLC circuit, so it implies that maybe it's a second order circuit. So how can I understand the order of the circuit? So the order of the circuit is essentially, assume that you are focused on the zero input case, when the input is zero, meaning that source is essentially short-circuited. There is a short circuit representing this. Then, can you set the inductor current, IL, and can you set the capacitor voltage, VC, in any way that you like? For example, assume this is short circuit. Let's make it short circuit. Can I say that IL is equal to 1 amperes, VC is equal to 5 volts? Yes, there is no conflict. If VC is equal to 5 volts, there will be 5 over R amperes going down. This was 1. 1 minus the remaining 5 over R will be going like this. And again, this voltage will be the voltage of this inductor, and so on. So there is no conflict. So it seems that I can set any numerical value for IL, VC independently from anything else. So that implies that these potential state variables are independent from each other. For example, if you think any other variable, let's say that VR or IR, okay? So clearly, if you put, instead of this, let's substitute, just for visual clarity, a voltage source VC of t, okay, representing this potential difference from here to there. And if I represent a current source or substitute a current source for this inductor IL of t, okay. Now it should be clear that whatever any other branch in this circuit, this is the only other branch, okay, its branch current or branch voltage can be represented as a linear combination of these two sources, because this is right now a memoryless circuit. So what does it say? Any other variable, IR, is dependent on IL and VC, our potential state variables. So we see that we have two independent state variables, okay, and any other branch voltage can be represented, or branch current can be represented by simply an analysis of a memoryless circuit as soon as we find these values or the functions for these state variables. Okay, so what did we achieve? We have achieved the following. After this, visual inspection essentially, because you don't need to, erase, draw one more time every time. So we have set the order of the circuit. We have determined the order of the circuit as 2. Okay, so this is indeed a second order circuit. Okay. So this second order circuit, we have seen how to represent this circuit in the state formalism. So essentially, the state equations can be shown that it is as follows. So this is quite easy to derive. It's much more easier than our examples. Okay. So this is a representation of the circuit. Of course, this is a first order matrix differential equation. Unknown is a vector. So this is my state vector, one more time. And this is my A matrix. A matrix. Okay. And this is my x dot. Rate of change of this state vector. This is my B vector. And clearly this is my only input. There is only one input. So it appears on the right hand side of this differential equation as expected. So what do I see? So I see the following. Rate of change of this, Vc, that means rate of change of the capacitor voltage. So rate of change of this first variable is equal to a linear combination of the state variables, okay, plus input is not affecting the first rate of change of the first variable, okay. But for the second one, again, a linear combination of IL dot is equal to a linear combination of the state variables through this A matrix essentially, and input is directly affecting with the coefficient of 2. Okay. Now this is again a second order differential equation because this is a 2 by 2 matrix, and our focus today is a solution of such differential equations. But the differential equation is never complete unless we provide some initial conditions, isn't it? So let me write this input. So how do I write the initial condition? Let me write it over here. So Vc0, 0 minus, let's say, IL0 minus is equal to some values, V0, I0, written like this. And I can represent this as state vector at time 0. So how do I visualize this? Well, I visualize this as a state vector. You know, it's something like a tip of this pen, for example, okay? This is a three-dimensional vector, but tip of this pen. I know that the tip of this pen is x, y, and z coordinates. At the beginning, at 0 minus time is something. And then I start moving this pen, so I'm applying a force, okay? So the force is this input, essentially. And this equation tells us that the rate of change of, let's say this is x variable change, okay? So if I push it this way, for example, there will be a change in x, there will be a change in y, and so on, okay? But we see that rate of change of this x variable, tip of this pen, is moving, okay? It depends on the position of the pen and also the input, okay? It depends on the position of the pen and the input. Actually, this is quite general. You can come up with such systems all the time, and you will see that this is a very familiar territory for many disciplines. But our goal is right now the solution of this type of differential equations. So what do I mean by the type of the differential equations? We are focused on this type of differential equation. Let's put this over here. Okay. Now, how can I solve this? Well, one way of looking at it, you know, can I write a scalar differential equation? So, as I have said, this one is, well, first order matrix differential equation. Okay. This is first order, but the matrix involved is 2 by 2. Now I would like to write, so let's write a scalar differential equation for one of these state variables. So let's select Vc of t. Okay. Vc of t. So what's the meaning of the scalar differential equation? Well, I should be writing a differential equation only Vc. And I don't know the order of the differential equation, but it will be probably 2. Okay. So how can I do this? So let me take derivative of this first equation. So what do I mean by the first equation? You know, essentially I have two equations written in this matrix form. The first one is Vc dot is equal to minus 3 times this, 1 times this, plus 0 times this. Okay. So I'm taking the derivative of the first row essentially. So what do I get? Vc double dot minus 3 Vc dot of t plus IL of t. Okay. So if this first equation is correct, then this has to be correct. Okay. Why? Because this state equation, differential equation, is always true for all t greater than 0. And I'm taking, derivative means just taking differences in time, essentially. So this should be also correct. So this is a second order differential equation, but I don't want to see IL. So I want to see only VCs and the input in the scalar differential equation. So what do I do? Now I can use this equation, IL dot. So IL dot is equal to, from the second equation, let's say this one. So IL dot is equal to minus 2 VCT plus 2 VS of t. Okay. So if I substitute it over there, then what do I have? I get, so let me write it like this, d square plus 3d, so substitute this, plus 2 Vc of t. So I'm doing this substitution over here for this. Okay. Is equal to, so this is left, isn't it? I have moved all the things to the left, so this is Vs of t. So this is what I mean by the scalar differential equation. Second order scalar differential equation. So in EE201, in the earlier course, you have already studied, RLC circuits, and we know how to solve this differential equation. But again, a differential equation won't be complete without the initial conditions. So, but since this is only in VC, I need the initial conditions at 0 minus. So I should, I should be able to, derive these initial conditions from the state equation itself. So how can I do that? Well, this is already given to me, V naught. And rate of change of VC at 0 minus, I can also calculate that. It's not a big deal. I can calculate it in terms of these initial conditions. But let's do not focus on that. Let's assume that this is V naught rate of change. Let's show it like that. Okay. Another numerical value, it has been given to us. So that is the end. So if I can write this scalar differential equation, since I know how to solve this, you can say that solution of the state equation is achieved through this indirect way. So I know how to solve this. I'm converting state equation to this form. But this is not the preferred way. You will see what I mean by that. But, so let's go ahead. So how do we solve such scalar differential equations? And this differential equation is called, maybe you will remember, CCDE, constant coefficient. This is differential equation. I think it's very clear. Coefficient is 1, constant, 3, 2. So what is this D? D is the operator showing the time derivative. So it's calculating the rate. Okay? So rate of change of this Vc at time t is d times Vct. So what's the meaning of differential equation? Well, the meaning of differential equation is this. Well, so this is an algebraic equation. You are trying to find x, let's say. Okay. So you do some operations, essentially multiply by 1 over 3, both sides. Okay. Then you get the value of x. Now, how about this one? Now you are looking for this. This is your unknown. You don't know this. You know this one. Clearly, this is your input to your circuit. This is the thing that you connect in the laboratory. Okay? If you have an AC source, this will be your AC source. If you have a DC source, etc. If you have a microphone connected to this RLC circuit, that microphone is producing some voltage, and that is your input to the system. Okay? Now, Vc of t is the unknown. So, what's the meaning of this? I need a function whose, let's say, initial value, let's say that there is continuity at 0 minus and 0 plus. At 0 plus value is equal to this, okay, from the initial conditions. I know the initial conditions of the system. And after the initial conditions, I'm looking for a function, 2 times the unknown function plus rate of change that function times 3 times double rate of change. So if you think about this is like the position of my pen. So 2 times the position of my pen, 2 times the velocity, 3 times the velocity of my pen, and this will be the acceleration. So I'm looking for a function. This is the reason, this is the main difficulty. Because this equation involves the position, unknown position is our interest, but rate of change of position is essentially velocity, and then we have acceleration interacting. Okay? So this is the reason that such equations, constant coefficient differential equations, always come up. Because when you write equations like F is equal to m times A is the acceleration, then you are looking at the position of a, let's say, mass, And then second derivative of that mass is acceleration. If you have some friction, things like that, essentially you have a differential equation. You know the initial position of the mass, you know the initial velocity of the mass. Let's say you try to solve this. Okay. So you always end up with some kind of a, in many cases, at least in the simplistic cases, constant coefficient differential equation type solutions, problems. So BC of t should be found. So how can I find this? Now, in this hour, we will be focused on the zero input case. We are going step by step. Our focus is right now. Our focus in this lecture is the zero input case. So what is the meaning of zero input? Well, I think it's very clear. Input is zero. Okay. Meaning that I have zero, short circuit one more time. Okay. Over here. So again, this will be considered as zero. So if the input is zero, that is also called the natural response of the circuit in the absence of external forcing, external input. So this would be, system will be excited by the energy stored in this, let's say, electrical components, and then circuit will react naturally according to its nature to these initial conditions, and what we expect is that initial energy stored in the system will be dissipating over this resistor. Okay. So eventually current and the voltage IL, VCT should be going down to zero. Okay. This is what we expect from the practice of this, similar let's say problems and circuits. So natural response describes how that asymptotic behavior is being achieved. Is it going down to zero by oscillations? Okay, it's called underdamped, or just decay, exponential decays, and so on. Natural responses covering that part. So zero input is zero, so we are looking at the natural response of the circuit to these two initial conditions. So let's see. Then the capacitor voltage, unknown from the differential equations course. We know that it is the homogeneous plus the particular, and this is a complete solution, isn't it? This is the general form. Well, homogeneous solution is when the right-hand side is equal to zero. Okay. So when right-hand side is equal to zero, we try to get this one. Particular solution is, well, we try to find a function such that this differential equation is satisfied when right-hand side is present. Okay, Vs of t is present. But in this example, sources in this differential equation, this is equal to zero, and you can say that, okay, particular solution is also equal to zero. Because if you insert particular solution of zero over here, zero derivatives, whatever, on the left-hand side, so you have zero function, right-hand side is also zero, everything is satisfied, you are happy. Okay. Essentially, in this problem, particular solution is also zero. Okay. Now, good. Next, how can I find this part? You may remember that we have a procedure for finding this. So we say that we are making a guess. Okay. So what is that guess? A times e to the lambda t. So I don't know the value of A, and I don't know the value of lambda. Okay. Again, you have seen such things before. Now, if this guess is correct, this differential equation, the homogeneous differential equation, should be satisfied, isn't it? So if guess is not correct, there is nothing else to do. You make another guess. So what do we do? Now you substitute guess into differential equation. So what do we get once we do the substitution? Now, second derivative of my, this time I'm focused on this homogeneous part, h. Okay. So I'm taking second derivative of this. So every time that I take the derivative of this, since it's an exponential function, if you differentiate with respect to time, t is the variable, then you're only scaling this function by lambda. Essentially, this coefficient is scaled by this lambda, unknown lambda. So then you have the following. Lambda square, there is a. If you take the second derivative, 2 times lambda, lambda is coming in the front 2 times, so I have lambda square. 3 lambda plus 2, and I have e to the lambda t. So I have substituted this over here and evaluated left hand side. So this is equal to 0, and if my guess is correct, this should be equal to 0, isn't it? For all t greater than 0. So if it is 0, I am done. This would be correct guess, equation is satisfied. There is nothing else to do. But how can this be equal to 0? Because I don't know the value of a and lambda right now. So can it be equal to 0? One observation is the following. Well, if you focused on this, e to the lambda t, let me sketch over here, as a function of time. So this is an exponential function, and you are looking at, let's say, t greater than 0 behavior. So it's either going like this, for example, e to the 2t, just exploding towards infinity, or it's maybe going down to 0 like this, e to the minus 3t, something like that. Okay. So what is interesting is that this function is not equal to 0, meaning that for any value of lambda, this is not equal to 0. So I can divide by this, whatever this value is for at any time, it's not equal to 0. Then if I divide it by e to the lambda t, I don't know the value of lambda, but I don't care because it's never equal to 0. Now I have this divided by a non-zero number. I have an equation like that. So what is interesting is that right now the t dependence of this equation is gone. So I have a time independent equation after this division. So I'm left with this. Okay, so how can this be equal to 0? Well, let's have this. I have two choices. A can be equal to 0. If A is equal to 0, isn't it? This is satisfied, this is satisfied, go back, everything is satisfied. But interesting thing is that when A is equal to 0, homogeneous solution itself is equal to 0. 0 times a number is always 0. But if your initial condition is not 0, if it is not 0, then you can say that, okay, this is not the solution that I want. Even though it satisfies the differential equation, I can never satisfy the initial conditions with this. Okay? So if your initial conditions are also 0, then everything is 0. Then solution is essentially 0 function. Initial conditions are 0. Homogeneous solution is 0. Right-hand side is 0. You have zeros everywhere. That is the solution. So this is the reason that this is called a trivial solution. Okay. This is trivial solution is the solution in the trivial case when we have 0 initial conditions and no input. I mean, as the name implies, this is the trivial solution. But in general, we are not interested in the trivial solution. So let me erase this. So let's go this way. So if A is not equal to 0, then what can I do? Well, the other case is lambda square if A is not equal to 0. This has to be equal to 0, isn't it? If A is not equal to 0, then this has to be equal to 0. This bracket, the second bracket, has to be equal to 0. So maybe you will remember, this equation is called characteristic equation. Okay? And the roots of this equation, -1, -2, they are very dear to us in the sense that these are called natural frequencies. So natural response I have mentioned. So this is a natural frequency. Okay? So the natural behavior of this circuit is ruled by these natural frequencies essentially. Okay. So is this the end? It's almost the end. But here's the case. How about the value of A then? Now I have found lambda as either -1 or -2. But how about this A? I have found the natural frequencies. It seems that A can be anything. It can even be 0. Okay, this is always satisfied. But A can be -5, A can be -1 million, +1 million, doesn't matter. So my homogeneous solution is then A e to the minus t, because of lambda is equal to -1. And how about this one? B e to the -2t. So I have made a guess like this, a single term. So I know that if lambda is equal to -1, Lambda is equal. This is satisfying the differential equation. We have just seen this. And lambda is equal to -2. This one satisfies the differential equation. And over here, these a's and b's, they can be any real number. Any number that you can imagine, no problems. So this differential equation is satisfied. How about their addition? Well, again, this is the linearity in action right now. Insert this one over here alone, insert this one over here alone, and add those two equations. It is equivalent to inserting both of them together over here by linearity. Okay, so that tells us that. So I have made a guess for this as this one, but I got two solutions. A superposition of those two possible solutions is also a solution. So once I realize that essentially from the linearity of this constant coefficient differential equation, so I get the general form of the solution. Okay, so AB, as you see, any. So again, the question remains, how am I going to find A and B? Well, we will be finding A and B from the initial conditions. So in other words, 0 plus value, okay, will be equal to, by continuity equal to this. And then from that value you will getting two equations and two unknowns. And that will be you will be solving at the end from the 0 plus values, and that will be the result. That will be the final answer for this second order scalar differential equation. So why am I focusing on this? Because of the procedure. So what is the procedure? You make a guess. Guess is classical guess, unknown coefficient, e to the lambda t. Okay. And then you substitute the guess and try to find what we call at the end natural frequencies, these lambdas. Okay. And then once you set these lambdas correctly, then you set these scalars, okay, coefficients a and b, such that you satisfy the initial conditions. Okay. So in many problems, initial conditions are given at not 0 minus, at let's say 0, okay, because of the continuity. Then you immediately write those two equations and you solve for a and b. Okay, so this is the procedure. Again, you may say that this is the end of this lecture because I have converted this differential equation, you know, to a scalar differential equation, and I got the solution as you see over here. But let's see. Let's see what we can do. So let's say that I don't want to do this conversion and I want to solve this differential equation. This is our state equation system. Okay. Again, I am focused on this 0 input case. This is 0. Don't worry about that part. So what should I do? Well, no surprises. I'll be doing something like, let me see. I'll be making a guess. So what is my guess? So this x is this vector, as we have said, vc of t, il of t. So let me have, for example, alpha 1, alpha 2, e to the lambda t. Okay. So previously, I had a scalar. Let me erase and rewrite. Previously, I had a scalar differential equation, and my guess was only for vc of t. Now, I'm making such a guess because from my earlier answer, actually we know this is the form of the solution. vc of t satisfies this, and if vc of t satisfies that, please remember in this circuit, this is 0 input. Then, so there is an exponential voltage with this rate lambda, let's say, on the exponent. And you can, by just looking at the circuit, that will be also affecting other branches. And then, by differentiation, multiplication, you can never get rid of this exponential because it's always, if you multiply a number by this function, you get the same function scale. If you take the derivative of this function, for example, we are calculating the current, okay? So this is Vc. Again, the same exponential is present, okay? So if you have an exponential voltage over here, you can feel that you have an exponential voltage over there, exponential current over there, with the same exponent everywhere in the circuit. So this is the reason that we are making such a guess. So there is a single exponent, this lambda on the exponent, which will be again natural frequency. And then we will be trying to find this lambda by again making a similar guess. Okay, so if this guess is correct, again, let's substitute. We are at this step right now. Substitute guess into differential equation. Okay. Now what do we have? So let me write this as x of t. Now I have x dot of t. What is x dot of t? X dot of t is time derivative of this. So alpha 1, alpha 2. So how do you take the derivative of this? Well, this is multiplying the first element, multiplying the second element. So if you take the derivative of a vector, okay, you take the derivative of every entry of this vector. So you put a dot over here, dot over there. But since this same term is affecting all of them, so you can also write this as this. Okay. And then let's erase this. So this is my x dot of t is equal to a times x of t, but x of t is this. Okay. So this is supposed to be satisfied for all after initial condition, for all t greater than 0. Okay. Now again, I don't know the value of lambda, but the same thing happens as we have cancelled over there, again a cancellation of this. So if I cancel this t dependence, again I have a time independent equation like that. Now if you remember your linear algebra course very well, now you can recognize this as this part. So what is this part? This part. Okay. So after this cancellation of the time dependence, so a times this alpha vector is equal to lambda times this alpha vector. Now, from the linear algebra course, you can immediately say that, okay, so I know these are called something special, eigenvalues of A, and this would be the corresponding eigenvector to this eigenvalue. Eigenvector corresponding to lambda. Okay. Okay. So this is the end of the analysis, but let's say that I don't recognize it immediately, but that will be our final answer. But let's say that I don't recognize it, but I try to, find my way like we did before, and I try to evaluate this solution such that at the end I'll be getting my lambda, a values, alpha 1, alpha 2 values, etc. So how can I do this? Now, let me move alpha 1, alpha 2, let me move this vector to this side. So I'm trying to satisfy the guess, as you see. So I have minus a times this alpha vector on the left side. How about this one? So this, I can put this lambda if you wish over here, doesn't matter. So I can put a lambda then. But here is something that we should be careful. Why do I say so? This is a scalar, this is a matrix. In our case, this is this 2 by 2 matrix. Okay. So this is not acceptable arithmetic for matrices. So how about this? We should be a little bit careful. I'm inserting an identity matrix over here. Doesn't do anything. But now with that identity matrix, I have this lambda I minus a. Okay. So if this is satisfied, then your differential equation is satisfied. The homogeneous part is satisfied. Very good. Now, right now, I am looking for the ways of satisfying this. So essentially, we are deriving eigenvalues and eigenvectors one more time from scratch. Lambda I minus a. So I don't know the value of lambda, obviously. I have no idea about this. And I don't know the value of, these are the parameters in my guess, as you see. I don't know them, I'm trying to find them. Okay. So, what should I do? Let's go this way. Now, I will be doing the following, this way. If lambda I minus a is invertible, so this is a matrix. So, for example, if lambda is equal to 10, you have a 2 by 2 matrix, like this one, 10, 10. But from this 10, you are subtracting minus a. So this will be 13. This will be minus 1. This will be 2. And this will be 10. Okay? If lambda is equal to 10. If 10 identity minus a is an invertible matrix, I don't know the value of lambda, but if it happens to be invertible, then I can calculate its inverse. Okay. Then you see that alpha 1, alpha 2, whatever this inverse is, I can calculate it because it doesn't matter, but at the end I'll be multiplying by 0. So this would be equal to 0. Again, this is a very dull solution. This is what we call again the trivial solution because I'm multiplying by 0. As you see, again we end up with a trivial solution. This is not very interesting. Lambda I minus a, the case of invertible, it's not very interesting. Now, how about the other case? Now, the second case. So let's go this way for the second case. So lambda I, lambda times identity minus a is not invertible. Okay. So what's the meaning of this? Well, this is equivalent to assuming that lambda I minus a, okay, this is equivalent. So what is this thing? This is the determinant. Determinant of lambda I minus a is equal to 0. Okay, sometimes we use these bars to refer to the determinant. So this is a great result in linear algebra about invertibility and so on. So this is the case. If it is not invertible, then its determinant of this lambda I minus a should be equal to 0. Then let's try to calculate this. What are the lambdas? As you see, this is, let me see, this matrix. So lambda I. So I'm putting lambdas over here. 0, 0. Lambda times identity is this. And minus a. This is a. Minus a is, I have 3. I'm adding this. Minus 1. Let me erase 0 then. I have 2. And this is already plus 0. That is it. So I should be calculating the determinant of this. Okay. So what is the determinant of this one? This times that minus this product. Lambda times lambda plus 3 plus 2. Lambda square plus 3 lambda plus 2. So we get the same equation, isn't it? We should be getting the same equation at the very end. So by the way, in your linear algebra course, this is also called the characteristic equation. Okay? You can remember from your linear algebra course that determinant of lambda I minus a is also called the characteristic equation. No chance, it's not a chance. So it has been arranged that way because they are referring to the same thing essentially. Okay, so one more time. We have seen that then goes this way. Then my allowable lambdas are minus 1, minus 2. So these are the lambda values making lambda I minus a, okay, this matrix, okay, non-invertible, okay. That is, its determinant is equal to 0. So then my solution, so let me write homogeneous solution, this was my guess, this one, okay. I'm trying to solve this homogeneous part, is equal to alpha 1, alpha 2, e to the either this, okay, or let me write beta 1, beta 2, e to the minus 2t. Again, I made a guess for a single term, not additive, but you can see that this is the solution, this one, first one. This is another solution, again by linearity. What do I mean by linearity? If you insert both of them into the differential equation, since differentiation is additively separable, you have two terms. If you insert them over here, so you multiply this matrix by this two terms over here, essentially, these two terms. Again, this is a linear operation. It becomes additively separable one more time. Then left-hand side, right-hand side are equal to 0 because individually these two terms are making the left and right equality. Okay. So that is the end actually. But still, I haven't found what are these alpha values and what are these beta values. Okay. Well, no surprises. They will be, again, no surprises. They will be related with, let's erase this, eigendecomposition of this A matrix. Okay. So let's try to find them. So again, let's write this a little bit fast. Lambda I minus A. Okay, it is this. Now, what was the case? So I'm looking for the following, isn't it? Lambda I minus A times alpha 1, alpha 2 is equal to 0, 0. Okay? So this is from my guess. So case number 1, if this is invertible, trivial solution. If this is not invertible and not invertibility leads to these specific values of lambda, and then for those ones I have another solution possibility. Now let's do the following. Let's assume that lambda is equal to minus 1. If lambda is equal to minus 1 in this equation, what do I have? I substitute minus 1. Again, if I make lambda is equal to minus 1, this will be a rank deficient matrix. So let's see, what do we have? Lambda is equal to minus 1. So it's lambda I minus A is conveniently present over here. So I get 2 minus 1, 2 minus 1, alpha 1, alpha 2 is equal to 0, 0. Okay. So as you see, we have two unknowns. You may say that we have two equations, but these two equations are the same. The first row, second row of this matrix equation represents these two equations, but equations are identical. So essentially we have two unknowns and a single equation. So again, this is an important topic in linear algebra. If we have such equations, linear equations, we are considering the uniqueness of the solution, number of the solutions, consistency of the equations, and so on. So for this case, so do we have a solution? Yes, we have a solution, but we have infinitely many solutions. Why do I say? So because alpha 1, alpha 2, if I select, for example, alpha 1 as 1, then alpha 2 is equal to 2. If I select this one as 1, 2, as you see, this makes it equal to 0. But I can multiply them by, let's say, k, any value. Okay? I can select first one as k, then the second one will be 2k. So for any k, this is also satisfied. Okay? So again, this is, if you check this, it's not different from doing this. Well, this equation is not different from finding a times alpha 1, alpha 2, lambda times alpha 1, alpha 2. Okay. So if you move this, actually we have done this a few seconds ago. So this is the eigenvector corresponding to what was the eigenvalue? Lambda is equal to minus 1. Okay. Now let's find the other one. Lambda is equal to minus 2. So we have called that solution the second eigenvector, which will be, it is supposed to be something like this. Well, lambda is equal to minus 2. 1, minus 1, 2, minus 2. Okay, now we have again two equations. Equations are looking different. But if I satisfy the first equation somehow, the second equation is nothing but it's guaranteed to be satisfied because the second equation is simply 2 times the first equation. Okay. So if you satisfy this first equation, if you multiply both sides of this first equation by 2, you get the second equation. So essentially this second equation is redundant. You don't need that. So that means that, again, I have 2 equations, but I have 1 equation and essentially 2 unknowns. Again, in linear algebra, this is a very big topic. Right now, this is a rank deficient matrix. It's not full rank. And then you are looking for a solution in the null space of this matrix. Okay. This is when the right hand side is equal to 0, this vector is the element of this null space. Okay. So many other things. For example, in linear algebra, dimension of the null space is an issue. For example, rank of this matrix is right now. Rank means number of linearly independent rows or columns. Okay. For example, this is this vector, column number 1, times minus 1, you get the column number 2. So you see that now these 2 columns are dependent. So then you are looking for this. If I have, so rank is not 2, that is. So if I have this vector, so you see that it's not 0, that means that this has rank 1. This is a rank 1 matrix at the end. So again, this is a 2 by 2 matrix. There is something called, for example, rank nullity theorem. In the rank nullity theorem, number of the columns minus the rank gives you the dimension of the null space. Okay. So 2 minus rank is 1. So dimension. So many things, as you see. So many things related with linear algebra. But you don't need to learn, or you don't need to know all of them at this instant, but you should be able to remember and maybe look at your linear algebra text one more time. Okay, let's find this one, beta 1, beta 2. So what is the solution? Now, if this is equal to 1, or let me have this is equal to minus 1, this is equal to 1. Let me move it this way. This is equal to 1, this is equal to 1. And let me, again, I can scale by, let me scale this by k1. Let me scale this one by k2, k1, k2. So this is k2 element of real. So this is the second eigenvector. Okay. Now my solution is over here. Okay. Now I have found alpha and beta vectors also. We are almost done. Now my solution will be K1, this thing, eigenvector of A, this, plus K2, 1, 1, 2t. So this will be my solution for t greater than 0. Again, I have calculated this homogeneous solution. So this satisfies this differential equation, homogeneous part. Now, how do I find K1 and K2? Again, I have 2 degrees of freedom. This can be any real number. I can set them in any way that I like. It satisfies the differential equation. So I'll be using this freedom to match these initial conditions. Okay? So that will be the finalizing step for the solution. So since 0 minus values, there is no input, is equal to the 0 plus values from our earlier EE201 knowledge, capacitor voltage is continuous, inductor current is continuous, because there is no impulsive input, as you see, we expect the continuity. Now you have then, very simple, well, let me write 0, just for the sake of simplicity, because 0 minus 0 plus, they're all the same. And then, if you wish, I can put 0 plus, then this equation, since it's always equal, it's valid for t greater than 0, it should be satisfied. Now I have the following then. Let me write k1, 1, 2. So substitute t is equal to 0 plus times, let me write this and then you will see. Okay. So if you substitute t is equal to 0 plus, so this becomes 1, this becomes 1, am I right? So this is the thing that we are going to use to find K1 and K2. So for example, initial condition is 5 volts, 5 amperes. So 5, 5 vector should be expressed as a linear combination of 1, 2 vector and 1, 1 vector, and these are the linear expansion coefficients. Okay. So, okay. So how can I write this? V0, I0. Well, I can, again, remember maybe my linear algebra course and appreciate it more at this instant. So I can write this as follows. This is 1. So what's going on? So in a typical high school kind of linear algebra course, matrix vector multiplication is done like this, or taught like this. First row, first column, second row, second column, first column, and so on. Okay. But how about this? If you focused on this K1 only, so this K1, maybe you have a very large value over here, think about it like that. So this K1 is affecting which elements of this matrix? Think about it like that, it's different. Well, we know first row, first column, K1 is affecting 1, second row, first column, K1 is affecting 2. Or if you look at this way, an easier way, assume that K1 is equal to 1 and this is equal to 0. Now it's clear at the end which one is affecting what. If you do this multiplication, 1, 0 is selecting the first column, isn't it? If you do this multiplication. So the first element is multiplying the first column. Second element is multiplying the second column. So this is 1, 2, my first column. This is my second column multiplied, so I can represent it like that. Well, this is nothing very, surprising, because at the end I'm writing the same equation one more time. V naught is equal to K1 plus K2, as you see. V naught is equal to K1 plus K2. It should be like that. But the thing is that, I can combine an equation like that as a matrix equation. So why this is good? Right now I can take the inverse of this matrix and I can finalize my solution. So I don't need to think about anything, and then I just apply my matrix inverse calculation. So if I go this way, so I'll be calculating the inverse of this matrix. K1, K2 is equal to 1, 1, 2, 1, inverse, V naught, I naught. I'm this at this point. Okay. So how do I calculate the inverse of a matrix? Well, you exchange 2 by 2 matrix. You exchange these two. Okay. Let me not confuse you. So both of them are 1, nothing to do. And you switch the sign. If this is positive, you make it negative. Okay. And then don't forget to put the determinant, 1 over delta. Okay, like that. What is the determinant of this matrix? 1 minus 2. 1 minus 2 is minus 1. So I've calculated the inverse of this matrix. So this matrix with the inverse sign is equal to this. Okay. Now, at the end, we are almost there. V naught, I naught. This is my initial condition. So I'm trying to find this two question marks, K1 and K2. As soon as I get that, I am done. So this would be equal to, now this minus 1 is, this is minus 1, this, I naught minus V naught. Then this is plus 2 V naught. This is minus 1 minus I naught. So my K1, K2 turns out to be that. Okay. 1 minus 1. So let's give it a check. So if I multiply this matrix by this inverse matrix, I should get identity. Is this correct? 1, 1. This, I get minus 1, divide by minus 1. This is correct. 1, 1, this is 0. 2, 1, this is 0. This one, you get again minus 1 and so on. Please do such trivial checks. Okay, if you do those trivial checks, you can catch your mistakes, in case at an early time. Okay, and what else? For example, how can I check this? In this equation, this I naught is affecting the second column. Signs of I naught should be different because minus 1, 1. Okay, they are different. These ones, they should be also different. V naught is affecting the first column. They should be different. Well, let me check one of them then. If this is minus 1, this is 2, minus 1, 2, minus 1, 2. I think it's correct. I mean, I did my best. I couldn't find any mistakes up to now. Okay, so we are done. Why do I say so? Well, K1 is equal to this. K2 is equal to this. And this is the end of this problem. Okay? So right now it's not the homogeneous solution because I have evaluated these coefficients. This is called the zero input solution right now. Okay? Because if you have left these coefficients undetermined, okay? So these coefficients, this is called undetermined coefficients, okay? Undetermined system of equations over here. If you fix those coefficients, as you see, such that this initial condition is satisfied, now you have solved your circuit problem. So what was my circuit problem? Input is equal to 0, short circuit. I have some initial energy due to this initial conditions, V naught, I naught, and for example, V naught is 10, I naught is 0, okay? So if this is, I have minus 10, I have 20 over here. So this is the solution. And this is a zero input circuit solution. Zero input circuit. Again, one more time. Many students confuse zero input solutions with the homogeneous solutions. Of course, they are looking alike. But zero input is the solution of a circuit, a physical circuit that you construct. Homogeneous solution is something like a theoretical tool. Okay? In this homogeneous solution, you are making the right-hand side of this differential equation 0, finding a generic solution, and then from this generic solution you use initial conditions and get the solution of your original problem. Original problem is circuit or solution of the differential equation. So that becomes the zero input solution. Now if I write this, for example, capacitor voltage, zero input. So what is this? I naught minus V naught e to the minus t plus 2V naught I naught e to the minus 2t volts. Always do some checks. For example, I'm expecting capacitor voltage to be continuous at t is equal to 0. This should be equal to, let's see. This is 1, this is 1 at t is equal to 0. So, as you see, I get V naught. Well, I have selected actually these coefficients such that that is, satisfied, isn't it? I have used this. So it's good. Everything seems to be in order, no problems. And then let's try to understand this solution. Again, nothing surprising, second order solution, natural frequencies, and so on. But before that, let me summarize what we have learned. Number one. So if I have this state equation system, okay, I have seen the following. The natural frequencies of the circuit or system corresponds to eigenvalues of A matrix. So how interesting. So why do I say so interesting? Because we know previously we have studied how to write this A matrix, and if you need to find the natural frequencies, then you can use a computational tool. For example, you can use MATLAB, and with a single eigen command you can get the natural frequencies. So we have lots of computational tools for calculation of eigenvalues and so on. So this is interesting. Now how about this? The general form of the solution is something like this: k1 e1 e to the lambda 1t plus k2 e2 e to the lambda 2t. Let's make it more general: kn en e to the lambda nt. Okay, something like that. So if this is n by n, then you may have n eigenvalues, which are the natural frequencies, and these e's will be the eigenvectors. So where, let's explain this, where a times ek is equal to lambda k times ek. Lambda k's are eigenvalues. Just we have seen this. EK's are eigenvectors. Okay. So in our example, so we have calculated this one and calculated this one as 1, 1, 1, 2, things like that. Okay, that was our solution. Okay, so what else? Now, how can I write this? Well, I can write this also, again, let's refresh our linear algebra skills. Also, I can say the following: x of t is an element of, let me write like that, span of, but how can I write? I don't have enough space. Let me use, I don't want to delete this. Let me write it over here. Also, x of t is an element of, this is the solution as you see, span of e1 lambda 1t, e2 lambda 2t, and en e to the lambda nt. Okay. So what's the meaning of this? Well, it means the following. So span of these vectors. Fix the t value to an instant. Now that means that you have a vector, you have another vector scaled by some numbers, and you have a picture like this. Okay. So you have e1 vector, e2 vector. Let's say that you have only two of them, like in our example. Okay. So span of these two vectors will be, well, these two vectors are spanning any point or any vector on this whiteboard. Am I right? Because these two are linearly independent vectors. So I can express, for example, this vector, this point, as a linear combination of these two e1 and 2 vectors with some scaling, as you see, things like that. So the span means all possible points that can be expressed in terms of linear combination of these vectors. So what do we see? So we see the following. Well, an initial condition is given to us. This is x0. Okay. Like in our case, v0, i0. That is this initial condition. Now, this initial condition vector at t is equal to 0. So I'm capable of adjusting these two vectors such that x0 vector, do you remember at the beginning of this hour we were discussing that this is the vector in 3 dimensions. I know where it is. At the beginning t is equal to 0, and then I'm trying to find where it goes under some input or under some dynamics and so on. Okay. So what we see is the following. This solution says the following. At the beginning your point is over here, and then this point let's say that these lambda 1 and lambda 2 are minus 1 and minus 2. So they're approaching this origin. Okay. So for example, how they are approaching? Well, this number as t goes to infinity, I have minus 2 over here. E to the minus 2 is, this number is getting closer to 0 and closer to 0. It's getting smaller and smaller. This number is e to the minus t. It's getting smaller and smaller. That means that this vector multiplied by a very small number as t progresses. Okay. So what we see is that now it has, again, the solution has two components. It's always a linear combination of these E1 and E2 vectors, but the length of this E2 vector, okay, it diminishes as t approaches, and eventually we get 0. So eigenvectors and eigenvalues, as you see, are very important because eigenvector enables us how you decompose this sum. Okay, because if you look at this vector alone, or the component of this solution, so that is, I'm talking about this component, you can see that this component of the solution, as t progresses, it goes towards 0. It gets smaller and smaller and smaller as t. But it's always along this direction. So this direction is very special. It does not move elsewhere, and it just stays on this E2 direction. And that is the eigenvector, in Turkish öz nitelik. Okay? So this is something very, let's say, basic to this A matrix. And similarly, eigenvalues are important because eigenvalues tells us how fast this component goes to 0 and so on. So our conclusion is, for any time t, we are lying in this span. It is equivalent to writing this. This is equivalent to writing that. Okay. So in this span, I am setting my initial condition by adjusting k1 and k2 up to kn. I am setting my initial condition and I stay in this span. Okay. So very good. A few other things and then we are almost done. So I'm erasing this, what we have learned. There will be a second, maybe what we have learned later on. Now, if I go back to this, let me write this. Okay, so so this is the solution. Again, only for the capacitor voltage. So I have something like that. So let me try to sketch this a little bit. Now, let's say that one of them is doing something like that. It starts from here, and the other one is, so this is the blue one. The other one is, let's say, the red one. This is the red one. So when t is equal to 0 over here, it takes this value, and so on. Of course, I see the, sum of them. What do I mean by the sum of them? This is this height above this height. My solution is, this height difference is getting smaller, something like this. Okay. So this is the zero input solution, and so on. Let me also mark this with black. Okay, so this is going like this. Now, you see that something very simple. Final solution is nothing but the combination of these two terms. So we will be calling these terms as modes of the circuit. So this is, let's say, mode number 2, blue one. Okay. And the red one will be mode number 1. Okay. Mode number 1. So you see the combination of two modes over here. Well, as you see, mode corresponds to the response in the final solution for an individual, let's say, eigenvalue, natural frequency, whatever you call. Okay. So let's write that. Modes correspond to the individual terms in the, let's say, zero input solution. Correspond to the individual term in the zero input solution. Again, one more time, corresponding to a natural frequency, to a single natural frequency. Okay, so natural frequency in this case was -2, this one was -1. I think it's very clear, mode number 1 and mode number 2. So what do we see? The final solution is the let's say, summation of these two modes, mode number 1 and 2. Now, if we check this, one of these modes is decaying faster than the other one. Okay. So how can I, well, you see that this one decays a little faster, isn't it? So how can I decide on that? Well, just check the exponent. So this is -2t and this is -t. So let's assume that this is equal to 1 over 10. T is such that this e to the minus t is equal to 1 over 10. Then what's the value of this one? So this will be 1 over 100, isn't it? This will be much smaller. It's the square of this. If this is 1 over 10 somehow, this is 1 over 100. So you see that this mode number 2 is multiplied by much smaller numbers. Okay? Because e to the minus 2 decays much faster. So that is the reason that this is called fast mode. Okay? This is called slow mode. Because in comparison to the other one, it is decaying slowly. So eventually, you'll see that the final response, because the fast mode decays down, converges onto the slow mode. Okay, red one is the slow mode, it converges onto it. So this tells us, if we have an nth order circuit, now we have n modes, and you can say that as t progresses, then there will be the slowest mode, and the system will be converging to the slowest mode. You can interpret it like that. Okay. So again, this eigenvalue, natural frequency, and these coefficients, which are related with eigenvectors, as you see, they become very important. Now here's a question. What should be, let me write this differently. Let's assume that we want to see only the fast mode in the solution, in VCZI, zero input over here. What should be the initial conditions? What should be the initial conditions to have that? Okay. So is this clear? First of all, what is the question? In a typical problem, you are given an initial condition and you sketch things like that. In other words, this is V0, you said it decays like this, it starts from this initial condition and so on. But since we have learned right now the concept of modes, so let's think about it. So if you want to have only the fast mode in my solution, so what should be the initial condition? So how can I find that? How can I find this initial condition? Well, I just want to see this blue term. Blue is the fast one. Okay. So the solution is very simple. Make this coefficient equal to 0. So I0 minus V0 should be equal to 0. Answer. Well, the coefficient of slow mode should be 0. I mean, almost like a trivial answer once you see this. Then V0 should be I0. Okay? Or in other words, if your initial condition is something like this, so let me say, sometimes we use this. This is called proportional to. Okay? If it is proportional to 1, 1, meaning that 10, 10, 5, 5, whatever it is, then this coefficient is equal to 0, and you are left with this fast mode. Okay. Okay, how about the other one? If you want to see this one, then you kill this one. How can I kill this one? So this time 1, 2, isn't it? If I set my initial condition for this, V0 is equal to 1 volts, this is equal to 2 amperes, or 10 volts, 20, okay? You get that one 0. So this is called, this topic, mode excitation. This topic is called the mode excitation. In other words, we see that this type of initial condition, 1, 1, 2, 2, whatever it is, okay? This excites this mode, and the other one excites the other mode, okay? So this is not very, well, maybe you remember that 1, 1 was also the eigenvector, and 1, 2 was also the other eigenvector. So we are ending up with the eigenvectors. Okay. So this shouldn't be very surprising, because let's see. Our solution was as follows. So if we have this, okay, so how was this? I0 minus V0, and this should be E1, isn't it? E1 vector. So corresponding to lambda is equal to -1. So lambda is equal to -1. Is it 1, 1? Let me give it a try. 1, 1. Okay. Plus 2 V0 I0, and I have 1, 2 vector e to the -2t. Okay. So let's see. Lambda is equal to 1, 2 vector. If I multiply by 1, 2 this one, I get -1, -2. Okay. Let me see. I think it's correct. Okay. I think this is wrong. This is 1, 1. So this should be 1, 2, and this is 1, 1. Let me give it a try. This is easier to check. If I multiply by 1, 1, I get -2, -2. Okay. If I multiply by 1, 2, this plus 2 times this -1, -2. Okay. I think this is right now correct. So this is E1. This is E2. Okay. So let's continue. Let's continue with this. Now, again, so if you want to see a single mode in your circuit, okay? If you want to see a single mode in your circuit, what should be your initial condition? So that means that this is the general solution, isn't it? So I can call this K1 if you wish. I can call this K2. If you want to see a single mode, I have this times that. Then make this coefficient equal to 0. Then you'll be left with this. Okay? So if that is equal to 0, now evaluate this at t is equal to 0. Okay? So if you evaluate that t is equal to 0, you have K1 times 1, 2 plus K2 times 1, 1. Am I right? So this is E1, This is E2. So at the initial condition time, at t is equal to 0, if you want to see a single mode, then, for example, if you want to see this mode, then k1 should be equal to 0, and you see that you are left with this eigenvector. Okay, you are left with this eigenvector. So if you set k1 is equal to 0, okay, then at the initial condition for this single mode excitation, I am left with this. So if you select your initial condition as the second eigenvector, then you are exciting this mode. If you select your initial condition as the first eigenvector, for example, you are selecting your initial condition as 1, 2 vector, clearly then k1 is equal to 1, k2 is equal to 0 in the solution, and you are done. Okay? So what we have learned. So what we have learned. Number 2. To excite a single mode of a circuit, the initial condition, to excite only a single mode of a circuit, only a single mode, the initial condition should be aligned with eigenvectors with an eigenvector, let's say, because it's a single, an eigenvector of A. Okay? So, for example, x0 should be proportional to ek, where A times ek is lambda k times ek. Okay? So, similarly, to excite, let's say, two modes, but only two, meaning that we are exciting not three but two modes. To excite only two modes, okay, the initial condition should be in the span of two eigenvectors. So we have learned the meaning of span. Two eigenvectors of A. So how can I say so? Please remember, what is the general solution? X of t is k1, e1, e to the lambda 1t plus k2, e2, e to the lambda 2t. It goes like this: kn, en, e to the lambda n, t. Okay? Let's say that in your solution you want to see only these two terms. And let's remember, this is the homogeneous solution right now, so I don't know these coefficients. Okay? So at t is equal to 0, evaluate this. So if your initial condition is, for example, k1 plus if initial condition is e1 vector plus e2 vector, meaning that k1 and k2, if they are selected as 1, 1, if your initial condition is satisfied, so that means the following: your initial condition is satisfied by selecting k1 is equal to 1, this is any number, k2 is equal to 1, and the rest all zeros. You'll see that this mode number 1 and mode number 2 will be excited. So that tells you that if your initial condition is in the span of e1 and e2, okay, it can be written as a linear combination of e1 and e2, then only these two modes corresponding to lambda 1 and lambda 2 eigenvalues will be excited. Okay. So again, we have seen the importance of lambdas. Right now we are seeing the importance of these eigenvectors in the solution. One last thing, and then that will be the end for all. Now I would like to discuss right now the state transition matrix. Okay. So how can I think about this state transition matrix? Well, this is the general form of the solution, homogeneous solution as you see. Okay. So I want to find the solution for an arbitrary initial condition. So what is the procedure that I follow? So this is the general solution, and then I say that x0 initial condition should be, you put 0 over here, should be written as a linear combination of these, eigenvectors essentially. Okay, so from the general solution, when t is equal to 0, you have k1, e1. K1 is multiplying the first column, we have studied this. K2 is multiplying the second column, all fine. Kn is multiplying the last column is En in this matrix, and so on. So here is my E matrix. Okay. So what do I do? So this is an eigenvector, n by 1, of n by n A matrix. So I put this column vector over here in the first column, put this over here in the second column, and so on. So this becomes an n by n matrix. So this is what I call this E matrix, n by n. Okay. So if this E matrix is invertible, then you get your K as E inverse of your initial condition. Okay. So these K's were the unknown coefficients. Actually, for the 2 by 2 example, we have calculated them. I0 minus V0, we had a parentheses like that. But this is exactly the same thing that we have done. So write this matrix, we have inverted a 2 by 2 matrix, you can remember in that calculation at this part of the board. Okay. So once we get these linear combination coefficients, meaning that if I can express this initial condition, tip of this board marker at time t is equal to 0, as a linear combination of these eigenvectors with weights this one, and then I can insert those weights, this is the final solution. This is how it moves at all times. Okay. So you may say that is the end. That is the end to find this solution. Indeed, this is the end. But how about this? Can I write right now my zero input solution as, I want to insert this K values into this equation, but how can I do it systematically? So how about doing this? Now I'll be writing again the following: E1, E2, En, okay, times K1 e to the lambda 1t, K2 e to the lambda 2t, Kn e to the lambda nt. Nothing has changed. Previously I was doing the same thing for t is equal to 0. Now this vector is multiplied by this scalar. First column is multiplied by this scalar. Second column of this E matrix is multiplied by this scalar. That is it. So that is good. So I have already called this E. Okay. So how about this? Now I'll be calling it again E, but I want to express this matrix like this: e to the lambda 1t, e to the lambda 2t, e to the lambda nt times k1, k2, kn. Okay. So this is a diagonal matrix, 0, 0. Okay. So can I write this part, this bracket like that? Well, high school way, multiply the first row by first column, you get this, which is good. Second row by first column, you get this. Or you multiply the first column by k1, you get this thing multiplied by k1. Second column by k2, add them, okay? You get again this. So this is correct. So the nice thing is, right now I have, I know this vector. So I can write my general solution, my zero input solution for an arbitrary initial condition, then like this. So let me use this part. E matrix, this going this way, times, there is a matrix, I will call this something, and I have E inverse times the initial condition. So this is this part. So how about this? This is the diagonal matrix in MATLAB notation. Lambda and T. So that is your final answer then. You say that my zero input solution is equal to this. Okay. My zero input solution is this. So in this solution, assume that you are writing a, let's say, MATLAB program. What do you need? Well, you are given this A matrix. You find the eigenvectors, eigenvalues of this A matrix. Then put all eigenvectors on the columns of this E matrix. Store it. Calculate the inverse of this E matrix. Store it. Then generate this diagonal matrix. On the diagonal terms, you have e to the eigenvalue times t, e to the eigenvalue times t. Then you have a 3 matrix stored. Multiply those 3 matrices. Of course, this matrix is changing by time because diagonal matrix has a t dependence. Okay, but doesn't matter. You do this multiplication, and then you may call this as, let's see, product of 3